Welcome to the pre-recording of lecture 28, which is the second part of the session 14, scheduled to be delivered on 14 July in the 8-week summer session. So this lecture closes off the 5th week in the course. It is also the third lecture on object-oriented programming, in which we are making our first acquaintance with this new way of programming, illustrated by Python. So with the slide presentation, I want to introduce the main concepts in how object-oriented programs are being built. And I will give some examples. In some sense, I believe a lot in learning by examples. The examples are coming from Turtle. So encapsulation, we can encapsulate Turtle objects. The other two examples are from mathematics. How can one represent polynomials in one variable? And then we have the inheritance, for which geometry lends itself quite well. Okay, let's start with object-oriented programming again. So we have given a formal definition, but you can also situate object-oriented programming in the evolution of the languages. The earliest languages, C and Fortran 77, uh, they are meant to program, to define and execute algorithms. So they are called procedure oriented. The second class of languages are object-oriented languages. I give examples. C is extended with C++. Smalltalk is an important language in the development of object-oriented programming. And then there is also Ada. So when we think about algorithms, we can think about pseudocode or flowcharts. When we think about object-oriented design, we are going to use the unified modeling language. Now, Python is a framework language, which means that it contains many classes that are very useful for a particular domain. So languages before the framework languages intended to provide only the basic building blocks. But then, of course, what happened was that compiler vendors provided all kinds of tools, um, and that led to several dialects of languages. So in working with a framework, and in some sense, Ada and C++, they also actually provide extra annexes in the case of Ada. In C++, there is the standard template library. So also there are modern versions of Fortran that also support more extensive programming than just the procedure-oriented languages. So this bullet presentation in three bullets here is just to give a brief overview of the different stages in the evolution of languages. All languages evolve, but there are some milestones. The algorithms in the 70s, the objects in the 80s and 90s, and then currently developed in the last 20 years, we have languages such as Python and Java. Um, Algorithms, objects, and frameworks. Um, for object-oriented programming, we are going to define classes, and classes, they are organized in a hierarchy. Here are very short definitions of key concepts in object-oriented programming. So we encapsulate data. We, in the sense that we limit the manipulation of the data to the methods that are defined in the class. So I will give an illustration with this how you can actually hide uh, data. So that is not new. So we covered information hiding with modules. So object-oriented programming and also in Python provides a mechanism for information hiding. The hierarchies, the natural way in which a hierarchy works is that you inherit from an existing class, which is called the parent class, to make a new class, to make a child class. We have seen examples with this with modules as well. So this is not so one module can use all the functions from another module. Um, and then there is polymorphism. Polymorphism is realized via redefining or extending, overriding, overloading existing methods. We've seen this in the first part of the session or in this previous lecture that we could do the operator overload. So these are the three important concepts in this lecture. So it's also the title of this lecture. And what I'm going to do is I'm going to illustrate via some well-chosen examples on how to do this in Python. We have encountered objects already very early on this course. So Turtle is an object-oriented version of um, having a turtle with a pen that you can put down and put up, and you can make very nice drawings with this. So what you here see is a cartoonish model of the Earth orbiting the sun. So the sun is at the center. The moon, so the Earth is drawn in red. So there is this ellipse of the trajectory for the Earth, and then there is the moon that circles the Earth. The trajectory of the Earth is here most interesting. Um, the the trajectory of the moon is most interesting. You see the spiral that is drawn via this model. So with Turtle, we can import the class Turtle, Turtle with a capital T, and make an instance of a turtle that we call the sun. And then we give the color of the sun yellow, and we check the position of the sun is at the origin. So that is the first drawing of the first object. So this is an application of wrapping. So we will make a drawing by having three turtles which represent respectively the sun, the earth, and the moon. It is still a top-down simulation. So later on in this course, I will address multi-threading. So here we have functions that tell the Earth to move, that tell the sun to move. So instead of working with these functions telling which planet when to do what, one one should use multi-threading. So this is a looking forward to what is next coming. Um, Python supports multi-threading, supports concurrency. Let me give an example of information hiding. In good design of programs, it is very important. Um, we talk about data attributes that are called a Python opposed to public. So the default is that one uses public data attributes. They are visible to every program that uses the object. But there are definitely cases where you don't want to do this. Here is an example of such case. If you represent a polynomial, then you can polynomial in one variable, then you can represent this as a coefficient vector. So here it's convenient that lists start at 0, so the constant term 7 is now at the first position. There is no monomial in x, so there is a 0 at position 1. There is a minus 3 because there is the monomial minus 3 times x to the power 2. And then you see that I need a lot of zeros to represent this polynomial of degree 8. So in this representation, the index of the coefficient in the list representation as a coefficient vector corresponds to the exponent. That's one representation. The alternative representation is to represent a monomial by a tuple. And then the terms in the polynomial are stored in a list. So we work with a list of tuples. Um, Which one is best? Well, actually, you may want to postpone that decision when you define your prototype. So the point is here to make the representation of the object polynomial private and to force that the user only accesses, only manipulate polynomials via the methods. So these are the methods to construct a polynomial, and then also we have the methods to compute with polynomials. There is also an important problem here why you may want to hide the representation from the user. There is the normalization problem. When is a polynomial 0? If you have the polynomial x minus x, it evaluates to 0, but you can store it as a sequence of two monomials. In this tuple representation, this is possible, for example. So if you don't want to decide in your prototype on a representation, you could also have multiple representations, why not? Then actually you can hide this by encapsulation, information hiding. Polymorphism. Polymorphism is very natural in Python via its dynamic typing. When we run Python code, the Python interpreter will determine the type of the variable, and that type, or here now we can say the instance of to which class the variable belongs. So we can check, we've seen examples of this in the previous lecture, is instance is applied there. So polymorphism makes that we can overload the string representation. So we have the string representation on a polynomial that we override. So the same method string here then takes different forms depending on the type of the object. I shouldn't mix type and object, depending on the class to which an object belongs, to which instance an object. So an object is an instance of a class, of which class the object is an instance of. Polymorphism also in some sense means that you can view an object as storing data, but you can also actually look at it as a function. So that's another type of polymorphism, which is very appropriate here for polynomials. So we can view polynomials as representations of data, a sequence of monomials, and we can see these polynomials as functions. We can overload or override the call method, and that makes the object callable. So if the call is defined for an object, then you can use the object as a function. That's very useful here. Okay, I will illustrate inheritance with points and circles. Now you could say that a polynomial is actually a monomial as well. So you could start by defining monomials, and then the polynomials kind of are derived from this. I will not do this. I will first um, or I will suggest this as an exercise. So this is a modeling exercise, viewing, first defining the class monomial, and then later on define the class polynomial. Okay, we make new classes from existing classes. So you can, this is a very nice tool to build complex programs in a very gradual fashion. So you can decide first on a basic prototype with limited functionality, but then you can extend by inheriting from your prototype. So you can derive new, you can make new classes, you derive classes from base classes. Um, So we distinguish between single and multiple inheritance. With single inheritance, the derived class inherits from only one class. So then the child has only one parent. That's very limiting. We can have multiple parents, so in multiple inheritance. That may lead to name clashes. So if parents have attributes with the same name, then one needs to be careful about this multiple inheritance. Here is an example of multiple inheritance. So a line inherits from a point. A line is thus a point and a direction. If you define a parabola, then geometrically speaking, a parabola consists of all points of the same distance from a focus and a line. The line is called the directrix. We will work out this application in a next lecture, and the following lecture still to be scheduled. But this is one of, so the TK stands for Tkinter. So we can make drawings like this. So you see here the directrix, the point and the direction of the line. In this parabola here, every point on the parabola is at the same distance from the focus, this point, and the distance to the directrix, not this point. So this is kind of an arbitrary point. Any point on the line can be used to somehow define the base of your line. So this is an example of multiple inheritance. The parabola inherits from the point, the focus, and it also inherits from the line. points and circles. So I developed that application because I grew a little bit frustrated when people define a circle as all the points at the same distance from the center. But then when they talk about a parabola, it's the algebraic representation y equals x squared plus some. It's actually then a polynomial in one variable defined by three coefficients. But in this way, you make parabolas that are extremely specific, where you have already where you force your view in a particular coordinate system. So here is another uh, application, a very simple application of inheritance. So a circle inherits from a point. It inherits the coordinates of the point. So we have the x and y, the coordinates for the center, and then there is one extra added attribute, that's the radius, and we have the extra method, the area. So it doesn't make sense, or we can't define the area of a point as being just zero. We can overwrite then the area, but the area of a circle with the proper formula. What's the point here? Well, you can fix once and for all the layout of a point. So when you define the circle representation of, when you define the string representation of a circle, you can rely on the string representation of a point. So for a point, it may be important that you go to a canonical representation of the point, and you can consistently use that throughout. So you can actually extend the functionality. So that is an example of extending. So you reusing the code, you're reusing the string representation of the point, but you are extending it with the added data attribute for the radius that you represent. This is actually the first example of inheritance. So this is simpler than the parabola. Okay, so we have inherited from the point to define a circle. A triangle inherits also from a point, and you can also have the coordinates of the corners of the triangle uh, taken on input. When you store the triangle, you will create 3 points with the input arguments of the constructor. You can also write an area function there. We have seen abstractions of stacks, and also there was an exercise of how to use a module to define an abstraction for a queue, a wrapper of a queue. This exercise 3 is here in some sense a modification of an earlier exercise, the wrapper module to a queue. So in class we defined a wrapper module to a stack. I could also have done the wrapping here where we define a class stack with the pop and the push operations. The exercise here is to define class Q, first in, first out, which has you could also use the pop, and in the implementation you should use the pop on a list, and the append. So the append is used to NQ. The DQ is the pop, where you pop from the front. So and this is another application of illustration of wrapping or encapsulation. You actually hide from the user the fact that a list is used. And I will show in Python how you can um, um, work with the hiding of the attributes, the data attributes. There is the encapsulation of turtle. So you can make a robot instead of having a turtle, you have a robot, and you can give the robot instructions, step forward, turn left, turn right. So you can do this on a grid. So the example that will be posted, the example that I will show, is a robot drawing um, um, a spiral. There are the other exercises which turn more into larger programming exercises. So instead of working with sun or moon, you could work with a planet class and inherit from that. This is a modeling exercise. Okay, so the exercises are in some sense the essence. There's a lot of terminology, but I hope it becomes clear that you can hide a lot of the complexity. So in the polynomial class, when you think about polynomials, you think about algorithms to add them. And you have the long division as well. These are important algorithms, but here they are hidden in the methods. Okay, so in the second part of this lecture, I will first use Jupyter Lab, and this is the um, Jupyter notebook that I have prepared. I'm starting with the class point. So class point is the name of the file, the dot with the extension .py that contains the definition of the class point. The help actually shows it. So this is our first class, if you like. And in some sense, a point is nothing more than a tuple. There is a constructor and a string representation. The string representation is in some sense already useful. So you can see the cohesion when you think about a point, you think about how to represent it. And that's mainly it. I will use this example to illustrate three functions which are useful. So I have the class point, which I'm importing now. I need to do this in order to define a point. So I define a point with coordinates 2 and 3. So I looked into the source code. Where is the source code here? So let me show the source code, the class point. Here is the class point. So the constructor defines the data attributes. There are xpt and ypt, so the x and the y coordinates. Um, Here you see the string representation, which uses the scientific notation with 4 decimal places after the dot. So I can directly manipulate, but often so you can check whether a variable has actually a certain attribute. So I can check whether the attribute xpt is there. I can get the value of the attribute, and I can also set the value of the attribute. So here I change the coordinate, the first coordinate 2 into 10. So this has some applications if you want to work with general variables. So if you want to use objects without actually objects that you for which you actually don't really have a fixed name. Think about the objects that are stored in a list, for example. Um, Verifying inheritance. The circle is a very straightforward application of inheritance. So I can check. So there is the is instance that you can check whether an object is an instance of a certain class. You can also check the hierarchy. So the circle is not a subclass of point, but point is actually a subclass of circle. So in order to make that happen, you have to do two main things. So you have to, in the class definition of circle, you have to explicitly give the point as an argument in the class definition. And in the constructor of the class circle, you must construct the point. So here you see, let me show the definition of class circle. So these are very simple definitions, but one has to start somewhere. So we are actually importing from the module point, from the module class point, where the class point is defined. I'm importing it. Um, so I can use it then in this definition here of the class circle in the declaration. I have to construct a point. So inside the class, I will have point. So I can refer to the point each time by using just point. So I don't have a self dot point, but I have a point whenever I want to use these coordinates of the center of the circle, like it is done here. So the string representation will print out the string representation of the coordinates of the center, and it will also print out on the next line the radius, the value for the radius. Then the area is a very simple method. It takes the radius, squares it, and multiplies it with pi. So it is important, and I also actually made this mistake. So if you want to compute the area, so if you want to see the string representation, you can use the str as it were a function. So you can do str of an object, just like you do print here. Print will actually print the string representation. You cannot do the area of C because the area is not a method that was previously provided via this underscore underscore. So that's important. So you have to properly call area as a method applied to the object C. And the C manifests itself as the self in the definition of the class circle. So the self here is the C in the usage in the Jupyter notebook. Okay, now let's go to a more involved application. So polynomials in one variable. So I can construct a polynomial by providing a coefficient and a power. I here had the word p also for power. A very basic version of the addition is defined. So here if I have, and also the string representation is rather very simple. I want to illustrate so the class itself is far from being complete. So we have defined all our operators overloading in the previous lecture. So it is a good exercise to actually extend the class with a multiplication. So here you see that where the algorithms come in. So you have the design of the class where you're going to override the operations, the arithmetical operations, but then you have the algorithms to sum and to manipulate the polynomials. So the polynomial is callable. So I can, even for this very simple example, I can ask what is the value at 3. So that's because the call is provided. A polynomial is stored as a list of terms, but even if I would know that there is terms, and even if I would know the double underscore, I can't really get to it via the has attribute. So it actually keeps saying that there is no attribute terms. Whereas if I look at the class polynomials, here you see that I am storing the polynomial as a list of tuples. So the string representation is very basic. So I'm storing here the sign as well. I haven't tried this with the minus. Perhaps I should have tried. So you have the um, string representation. So if there is nothing there, then I still will return 0. I will not return the empty string. Um, there is the addition of the monomials. So here, this is already a non-trivial algorithm. I'm actually not. Okay, in the remaining time that is left, let me now explain what was on the slides, the first example. So the first example was on the application of encapsulation to represent a polynomial, where with the encapsulation, so here is the relevant slide again, we want to hide the representation of the polynomial. So encapsulation means that the data is manipulated only via the methods in the class, not directly via the data attributes. So in Python, we can do effectively on information hiding. There are, um, so there are, I motivated this here with the uh, differences in the um, representation of the of the of the objects. You also want to you also may need to resolve the issue of the normalization. So if the deciding whether two polynomials are the same is a very related problem. So in symbolic computation, this is no longer trivial. Um, so in this lecture, we focus on the aspects of object-oriented programming. It's not my goal to give a complete working version of a polynomial class. So for that, I would refer to computer algebra systems. But this is a very nice application, a very nice illustration of hiding data. Also of polymorphism. So here you see the definition of a polynomial. So when we call the constructor, we essentially make a monomial. And we make a polynomial by adding the more and more monomials to it. So a monomial here consists of a coefficient and a power. So that's the tuple representation, which is quite natural. So I mentioned polymorphism too soon. So here is the polymorphism with the string method. So when you print a polynomial, you actually show the string representation. That works the way it works because the underscore underscore str underscore underscore, this method was defined inside the class poly. Another aspect of polymorphism is that actually we can view our objects as functions. by making them callable. If we give a definition for the underscore underscore call underscore underscore, so if we are coding up the algorithm to evaluate a polynomial, then we can uh, ask for the value of the polynomial in a very natural way, as if the object were a function. And the most important point of this example is indeed the information hiding. So we are storing the terms in a list, and I'm with the statements in the code cells 22 and 23. I'm illustrating that even if you would know, and we actually are knowing, I will show the definition of the class. So even if we would know that there is a terms, we can't really do anything with it. So terms is preceded by two underscores. And that makes that the data attribute is private opposed to public. So let me show the constructor. So in the constructor, we define the data attributes. So here, if we have a zero coefficient, and the zero coefficient here is done with a test, a very plain test. So I'm assuming here that the coefficients are all integers. So if the coefficient equals zero, then the list of terms is empty. Otherwise, I'm storing the coefficient and the power of the first monomial. So when I write a polynomial, I write the terms one after the other. I can check whether the list is empty or not as well. There are many alternative implementations. But if the result is still the empty string, I'm returning the string with zero in it. So I want to show the empty polynomial as zero. And here you see the addition then of two polynomials with a helper method. So addMon is a helper method that adds a monomial to a polynomial. So you see that the polynomial implementation is actually the polynomial addition is defined by repeatedly adding a monomial to the result. So I have the self and the other. I loop through all the monomials of the first operand, so that's the self, and I then loop, I add each time calling the addMon, and then I also add all the terms in the other. I was in a hurry when I defined this, so algorithm-wise, this is not very good. So the emphasis is here on the data hiding, not on the algorithm development. Here you can see that I do not normalize my expressions in the sense, my polynomials, in the sense that it would have been nicer to sort the polynomials on the degrees. So that would make for a much quicker addition and perhaps also a better algorithm, and certainly also a better algorithm. I do compare the degrees, so whenever there is a new monomial coming in, I compare the degrees. If the coefficient becomes zero, if the new coefficients become zero, then actually I delete the corresponding term. So I'm not going to store any monomials with zero coefficient. So you see the topic of working with polynomials is actually a topic in computer algebra. So this goes a little bit beyond the scope, but you can see that we can hide the complexity of the addition here. The other thing is that I have to show the algorithm to evaluate a polynomial. So also here, this is not the most efficient algorithm, but it is the simplest one. So I loop over all the monomials of all the tuples in the list of terms, and I'm adding up the coefficient multiplied with the variable to the power as defined in the tuple. Okay, so this is a very basic, incomplete version of a polynomial, illustrating the callable object, again the operator overloading, what we have covered last time, and the information hiding. So we have a private data attribute here in the terms of a polynomial. So now I'm really hiding from the user that I'm using a list. Okay, so I'm done with this. I just should flash up the wrapping of the turtle. So there is the program that has the simulation for the uh, sun, earth, and moon. So I make here three turtles. So I'm using object-oriented programming here, but in a very functional way. So this should have been done with multi-threading properly. And we may go back to this, but this is if you are interested in making these spirals. So there is a main program where I'm actually using also the three planets. They are just the names for the turtles, the referencing to the turtles. But I'm still using them as turtles. Just to indicate here how um, the um, turtle actually worked within the object-oriented framework. Then there is the wrapping. So there is the robot. You can encapsulate a turtle. So you can make a robot which actually functions now as an object that encapsulates a turtle. So when I make a new robot, I'm actually making a turtle. And here, this is not inheritance. I'm not inheriting, but I am making a data attribute that is a turtle. I call it Bob. Could perhaps better call it Bot. And I have the attributes of the robot that will work over a grid. So here now we have a grid of distance d. So that's the step that the robot takes, and there is a direction. So earlier in the lecture I defined a line as a point and a direction. So that's also actually the state of the robot. So you can use an object, a class to define, to encapsulate, but also to encode the state of your object. Now, of course, this is also in the in the turtle. So, in some sense, this is an encapsulation where you let the robot, you name the robot here Carl, and the robot steps and will draw a spiral. Okay, I hope that the three main concepts of encapsulation, inheritance, and polymorphism are now sufficiently clear. So starting with the very short definitions in the beginning of this lecture and how we have used the three concepts in the examples in this lecture.